question 2, they want you to refer to the equation why this is redox. So a redox is a combination of oxidation plus reduction. So it's two of these together. So you cannot just explain for one without the other. All right, you got to explain for both of them in order to show that it's redox. When I went through the O-level syllabus, I actually found out that oxidation number is no longer a thing. You know, it's no longer something that is expected from O-level. So I guess if you are covered in school, please use it, because there's no examiner from Cambridge who are marking your paper. They are stupid, all right? I mean, they know the chemistry. Oxidation number is a valid chemistry, and then it's a valid chemistry in addressing redox reaction. So even though it's not in the syllabus, you're more than welcome to use it if you know what you're talking about. Yeah. In fact, it is related to gain and loss of electrons. When we talk about oil rig, we talk about this acronym where oxidation is loss of electron, okay, and reduction is gain of electron. When you lose electrons, your oxidation number will increase because you are losing negative charge. You're losing negative charge, so your oxidation number will increase. Think about your metal. Your metal atom on its own is just oxidation number 0, because the oxidation number of an atom in its element is going to be 0. So copper is 0 there as well. But then when you give MgSO4, that is a SO4 2-. I hope you know that is the formula of sulfate, meaning to say the Mg there is Mg2+, and then the oxidation number of a metal ion is the charge of that ion itself. So there's just Mg plus 2. Similarly for that, there's copper plus 2 there. So going from Mg0 to Mg plus 2, your oxidation number has increased. That is oxidation. But then how does the oxidation number increase? From 0 to plus 2, it means you must have lost electron. And loss of electron is oxidation. So I hope you can see that this is related to changes in oxidation number as well. So without wanting to go into oxidation number, you are already going to oxidation number just by talking about, you know, this loss and gain of electrons. I don't know how the syllabus works. I might have to study in more detail, but there's no reason why you shouldn't be taught oxidation number, because it's a very important skill set. There will be disadvantages to you if you do go on and do advanced chemistry at A-level. Anyway, I already explained it, so I can say the magnesium, oxidation number of the magnesium. Oxidation number of Mg increases. So you got to specify from Mg0 in Mg2, Mg plus 2 in MgSO4. This is oxidation. Okay, oxidation number of copper decreases from plus 2 in CuSO4 to 0 in copper. This is reduction. So I've shown both steps there. What you could do, this is an alternative, because you might not have done oxidation number. You can do it in terms of electrons. The Mg goes to Mg2+. I don't include a sulfate because these sulfate are spectator ions. These are aqueous, meaning to say they are soluble. So you get Cu2+, SO4 2-, Mg2+, SO4 2-. You can cancel out the SO4 2- because they are spectator ion. Okay, in fact, then they will give you plus 2 electrons. So you have loss of electrons. You show that, and that is oxidation because you involve loss of electrons. And the other one is copper 2+, plus 2 electrons give you copper. That is involved gain of electron. That is reduction. In fact, both of these will allow you to construct the ionic equation. I think I just told you. The solid do not dissociate, but these dissociate into the ions, and the SO4 2- are what you call spectator ions. There exists SO4 2- here, there exists SO4 2- here. You can cross them up in your ionic equation. So what you're going to get is you're going to get Mg solid plus Cu2+ aqueous, give you Mg2+ aqueous plus copper solid. Okay, what is different really is you don't really need to have the stat symbols. I just include it because, well, I like to, and I can see it from the equation, all right? But you don't really have to, yeah? Because they don't specify in the thing. But the important thing is it's balanced, and the way to think about it is these are the two half equation, because each half represent oxidation here, this half represent reduction here. If you combine the two equations, you can see the two electrons cancel because the electrons here are on the left, on the right, the electrons here are on the left. When you add oxidation and reduction together, the left plus the left equal to the right plus the right. If these equations are balanced, if these electrons cancel out, your equation automatically balance. All right. Next bit, you want to make pure copper by electrolysis of aqueous copper to sulfate. This is a O-level case study. If you do intend to study A-level chemistry, you gotta remember this example because it's also an A-level case study as well. Yeah, you gotta label a label diagram for this electrolysis. Electrolysis require energy, so I'm gonna use this to represent power. So the shorter one represent minus, the longer one represent a plus. Okay, I will connect it to an electrode. Okay, these are what we call electrodes, and I will have them immerse or soak in electrolyte. My electrolyte will be copper 2 sulfate aqueous. Okay, now the important thing really now is this is negative because this is the shorter end, negative terminal. This is positive terminal. Okay, what do you call negative terminal and what do you call positive terminal? Positive terminal attracts let's go negative first. Negative terminal is negatively charged. It attracts positively charged ions. Positively charged ions are called cations. So cations will be attracted here because cations are positively charged. So this is called cathode because cations go there. This is the anode. Okay, I already labeled the electrolyte, I already have the power. Now I really need the material of the cathode and the anode. One is pure, one is impure. I want to get pure copper. All right, you have two equations. What you want at the cathode is you want reduction at the cathode. Red cat, right? Reduction happen at cathode. What is reduction? Well, reduction involves gains of electron. So you need to gain electron at the cathode. You need to gain electron at the cathode because this is what you want. You want pure copper at the cathode. Okay? How? You need to gain electrons. What needs to gain electron to give you copper? Well, it's the copper 2 ion, which is copper 2 plus 2 electrons. That will happen at the cathode. Reduction happen at cathode. You deposit pure copper at the cathode. So that one will be pure copper as the cathode, which means this is the impure copper as the anode. Alright, and what happened at the anode is you will get the impure copper giving you copper 2 plus 2 electrons. You get oxidation at the anode, and oxidation involves loss of electron. You lose electrons by having that plus electrons on the right hand side. Okay, so they all make sense really. And this color will not change. That's why they are asking you observation there. Oops, sorry, they don't asking you that. What you will see is you might get some anode sludge because of impurities forming at the bottom of the anode. So they don't go to the cathode at all. Only the Cu2 plus go to the cathode and they give pure copper there. You can get anode sludge down there. What you could see also is that the size of this will get smaller and the size of this will get bigger. And this solution is colored because it's aqueous copper to sulfate. It's pale blue in solution, but it will not change in color because the copper here is not from here. The copper here is from here to here. So you're migrating the copper from the anode to the cathode. Overall, there is no change in the concentration of the electrolyte. There is not used up. This copper 2 plus are not used up at all. All right. Just a bit of observations because when I saw this observation, I thought they were asking you to write down some observation of what you would expect to see as this electrolysis proceed. Yeah, so there's technically a very good question as well. Anyway, so what observations are made when you add aqueous ammonia to copper 2 plus slowly with mixing until no further change occur? So until no further change occur, you should know is that with ammonia or with sodium hydroxide and pepper 3 qualitative analysis, you got to think about in excess what happened. That's why it's not just the first thing that happens. So the pale blue precipitate will form. You know that's the first thing that will happen, right? In excess NH3 aqueous. the pale blue precipitate will dissolve. I hope you have done this practical before, because this is a very, very important observation that you must never forget, because it's very important. It's so important that even upper 6 students have to cover it again in A-level. Seriously, yeah, okay. And then the idea is that you don't have that table of data given in theory paper, so you gotta know the underlying observation, the chemistry involved. Yeah, so that pale blue precipitate dissolve, and that's not good enough because you want full observations in chemistry. So they do dissolve to give a different kind of blue actually. So if you have not done this, please ask your teacher to show you, because this is a very, very important observation that you should see. Yeah, it's a dark blue solution. It's a very different kind of blue, but importantly, precipitate dissolve to give you a solution. All right. Next bit, magnesium can stop iron from rusting. So this is the idea of sacrificial protection. I think in the other paper, the paper 2-1 component, similar question was being asked, but it was zinc and iron. So the idea really is just reactivity series. So magnesium is above iron in the metal reactivity series, which you should know as potassium, sodium. I nearly write SO for sodium. Okay, sodium is Na. Potassium, sodium, calcium, magnesium, zinc, aluminium, iron, blah blah blah. We know magnesium with iron there. So magnesium is higher up, and you know higher up is to do with more reactive metal there. Therefore, magnesium will preferentially gets oxidized by air. And when I say by air, it's actually the oxygen in the air, because the nitrogen, which is nitrogen triple bond there, very strong bond, doesn't react most of the time. Yeah, okay, unless in Haber process you have catalyst, you have high enough temperature, you have high enough pressure, then you can force it to react. Okay, but not naturally. Okay, preferentially get oxidized by air instead of iron. Okay, so this is the side reaction. So when the magnesium reacts with oxygen, so Mg plus O2, instead what they will get is you get MgO. Any equation you write has to be balanced. That is a wrong equation because it's unbalanced. So you gotta balance it with a half there, because there's only one oxygen, and 1/2 times 2 is 1 oxygen. You cannot change the formula of O2 because it's diatomic molecule, but what we can do is you can use fractions. If you don't like fraction, you just multiply the whole thing by 2. You're going to get 2, 1, 2. All right? So next is about electrolysis. So platinum is an inert electrode. So it's not supposed to react at all with any of your whatever product you're supposed to get. So they say that oxygen is formed at the positive electrode. So positive electrode will attract cations. Okay, so it attracts anions because anions are negatively charged. So that's why you are attracted to the positive electrode. Therefore, positive electrode is also known as anode. Okay, whereas negative electrode attracts cations. Cations are positively charged. That's why your electrode is negatively charged. The negative electrode is also known as cathode. All right, so where does the hydroxide come from? When you break it down, you have aqueous CuSO4. Okay, so the ionic compound give you this, but the aqueous will give you the H plus and OH minus. You have H plus and OH minus in water molecule, but it has pH 7 because the number of H plus ions are balanced out exactly by the number of OH minus ions. Okay, so from water, where does the water come from? Well, when you have aqueous solution, when you have aqueous solution means that you have water because you dissolve it in water. That's what aqueous solution means. Yeah. So we know the hydroxide goes to the anion. Sorry, it's an anion. It goes to the anode, and therefore it will do oxidation. where oxidation is loss of electron. So you lose electrons at the anode because you get oxidized, right? And the oxygen there is -2, the oxygen there is 0. So how are we going to balance this? You do need, if you put 2 there, then you have 2 oxygen, and then extra oxygen, so it cannot be 2, yeah, okay? So we're looking at 4, then we have 2 of that, then 2 oxygen give you 4 oxygen, 4 hydrogen, -4 charge, no charge, you need 4 electrons, okay? So as for part 3, I hope you can appreciate that in the metal reactivity series, we talked that the more reactive metal, okay, and the less reactive metal. So in those reactivity series, we talked specifically, you will have known that the more reactive metals will be preferentially discharged at the cathode, okay? So preferentially reduced. Okay, whereas when we talk about non-metals, okay, we talk about the lower they are in the non-metal reactivity series, I suppose. Okay, think about it. Okay, they become more easier to be oxidized. Okay, you're going the opposite way. Actually, when you go to do A-level chemistry, this will make more sense where we put values to it. Okay, but the more reactive the metal, okay, and therefore the in the other direction, they prefer to be more and more oxidized. Okay, we are talking about things at the anode. Okay, so oxidation happens at the anode. So we can say in terms of the ability to be oxidized. Okay, so not the sulfate ions are discharged. Okay, so we can say that the hydroxide ions are more easily oxidized compared to sulfate. If you have a look about this qualitative thing I just talked about, okay, if you are more easier to be oxidized, you are the one that will be preferentially discharged at the positive electrode because that's where the oxidation happens. Yeah, okay. I mean, it's the same way where you always talk about the more reactive metal gets reduced, that's why it gets discharged at the cathode. Yeah, so the 4 ions present, they are the H plus and the OH minus, the copper 2 plus, the SO4 2 minus, right? So as the electrolysis proceeds, why does the solution become acidic? Okay, you use a platinum electrode, right? So you lose the copper 2 plus and then you lose the hydroxide ions, okay? But this is the key thing. The hydroxide ions get discharged, okay? So the hydroxide ions, they even asked you to write the equation previously, yeah? Gets discharged as oxygen at the positive electrode, which is the anode actually, but there's no point thinking about it. I mean, really say it's positive electrode there. Therefore, less OH minus in the solution mixture, okay, or in the electrolyte. Therefore, more acidic. As you get less and less hydroxide, therefore you will have more and more H plus. Okay, so less OH minus. Okay, maybe I can compare with the H plus. Okay, so the fact that we have equal number of H plus and OH minus previously, okay, less OH minus in the solution then H plus, or you can say since this one is being discharged, you have more H plus than OH minus now. Okay, then H plus, therefore solution becomes more acidic. Previously, when you just have water, H2O aqueous solution, the number of H plus balance out the number of OH minus. That's why you have neutral pH. Yeah? As for why the blue color fades, what causes the blue color? It's all come down to the transition metal ion. Okay, so since the copper 2 plus is discharged at the cathode as copper metal, lesser copper 2 plus in solution that contributes to the blue color, therefore less blue. Or you can talk about the color fades away, so it becomes lighter and lighter, yeah.